This video is to show a technique for design and implementation of a monoband half-wave dipole antenna that's matched to 50 ohms. The design tool that I'll use to demonstrate things is SimSmith. And at this point we've got the half-wave dipole modelled in element L of the SimSmith model. It's set up for a feed point impedance of 65 ohms at resonance, that is 65 ohms resistive at resonance. If we look at a plot of the impedance, the resistance at the feed point varies slowly upwards from around 65 ohms to a little over. So it's quite slow changing in this relative bandwidth, whereas the reactance line increases quite quickly relatively and crosses through zero at the resonance point at 14.2 megahertz. Let's have a look at where that sits on a Smith chart centered on 75 ohms. The reference impedance here is at 75 ohms. So there's the antenna feed point at the frequency selected here, 14.2 megahertz. And you see it's 65 ohms. But we want to match that to 50 ohms. Now, almost integral to the dipole is a balun, and the balun has 0.8 of a metre of 110 ohm velocity factor 0.7 twisted pair wound around a ferrite core, and that's modelled by the T1 element shown in the lineup. Let's enable the T1 element, and you'll see that now the impedance looking into the T1 element's transformed. It's now looking like 70.3 plus J 24.3. We can then add a 75 ohm section to transform the impedance, but it would be convenient if the VSWR on the 75 ohm section T2 here was 1.5 to 1, because there will be points along the 75 ohm line where the impedance becomes 50 plus J0. But we want to excite that 1.5 to 1 VSWR for a start. So let's have a look at a constant SWR circle on the Smith chart. Our impedance looking into the balun is just shy of the 1.5 to 1. So let's detune it a little bit to push that impedance. Whoops, goes around pretty quickly, doesn't it? So we need to move in quite fine steps. So if we move that finely, we can take that out to about the 1.5 to 1. This is VSWR 75. The impedance at this point is 72.5 plus J30, but the SWR with respect to 75 is 1.5 to 1. We can then use a series line section of 75 ohm line to follow around this constant VSWR circle. So we'll turn the SWR circle off so that it doesn't obscure things, and we'll insert 1 metre of this 75 ohm line. Now I've configured this simply to be velocity factor 1, 75 ohm, zero loss. So we're looking at a lossless line, and we're looking at the electrical length showing here. So we turn on T2, and there it is, it's hardly moved. Let's increase the length of this and see what happens. Okay. So we'll enable a length of this T2 line now to follow it and observe what happens. So you'll see now we have the impedance looking into 1 metre of the 75 ohm line, which looks into the balun 110 ohm line and then to the feed point. Let's increase the length of this, and it's actually following around the VSWR 1.5 circle on the Smith chart. And eventually we find that it comes back here across the real axis at 7.689 metres, and the impedance looking into it is 50 ohms with almost no reactance. If you fine-tune that, you can make it 0. So there it is there. We now reach 50 ohms. Now it's interesting to look at the path that we've followed. So we detuned the antenna a little to move the impedance such that this impedance here, looking into the balun, was on the 1.5 to 1 circle, and we then adjusted the series section to bring it around to 50 ohms. So that's the matching scheme. Now we can have a look at what happens here with a scan. So I've got a sweep enabled, and we can look at what happens with the scan or the sweep. So the cyan line here is the dipole's native feed point impedance. Then it's transformed by the balun's 1 metre of 800 millimetres of transmission line, and that's the magenta line. Then it's transformed by the series section around to here, and that gives us the green line for the sweep. Okay, so let's now have a look at the VSWR plot reference to 50 ohms. So I'll change this now to 50 ohms. So let's have a look at the VSWR plot reference to 50 ohms. Firstly, changing this to 50 ohms will shift the Smith chart to a new reference, and you'll see it comes around here to the prime centre at the match point. And if we look at the VSWR plot, there's the original dipole response, which didn't get much below 1.4, maybe 1.3, about 1.3. And the response looking into the 75 ohm section now is the green response, and you can see the bandwidth and the response of the VSWR curve there. Now, it's not possible to calculate the losses from this model because I've used lossless line for T2. I have reservations about the line loss model in SimSmith, particularly when it relates to things like RG6, which would be a candidate for this. And there are practical problems with RG6. Some of the product that's sold in the market's got such a thin copper cladding on the inner conductor that it doesn't give copper-like performance and might not compare with stock characteristics of lines anyway. And the other thing is there are aspects of the model in SimSmith that potentially have troubles with composite inner conductors, that is copper-clad steel, for instance. Okay, so there's the design. So to implement this, what would you do? You'd put the dipole up, you'd measure and model the actual balun you're going to use. Let's change this out to, say, 9 metres long. You'd initially build it with too long a piece of 75 ohm cable. We'll turn the sweep off. So you build it with too long a piece of cable, and you would look at the VSWR looking into the 75 ohm line. So looking in here, you'd be looking at VSWR 75, and you want to set that, we'll have just change this, set that to about 1.5. Now you can do that with a VNA, changing the reference impedance, or an antenna analyzer that supports the same thing, or just a 75 ohm SWR meter, which is what I used 50 years ago when I started using this technique. So you make it a bit too long, adjust the dipole length to get 1.5 to 1 SWR on this 75 ohm section looking into it. Then you can measure the impedance and calculate how far to shorten this 9 metres. And this 9 metres is electrical length, remember. Or you can just successively reduce it till you see, monitoring your SWR with a 75 ohm indicator, be it a VNA or a SWR meter, just simply, once you've adjusted the dipole to get 1.5 to 1, so you then connect a 50 ohm instrument to it, and the SWR indicated here at 9 metres, 1.37. But as we decrease the length, we'll see that SWR comes down, and you see in the right-hand display the impedance at the end coming back to the centre of the chart, and there we've got a pretty good match, and we've found the length that works. Now in fact this length of cable has some loss, and it takes a little bit of tweaking to interactively get to this, but measuring the 1.5 to 1 from that input to that 9 metres, say, of cable, it gets you pretty close to then switching to 50 ohm indication, shortening the cable progressively until you get the cable that gives you a very low VSWR with reference to 50 ohms. There you go. Now, having set the length of this T2 for a 50 ohm input, 50 plus J0, you can then use an arbitrary length of 50 ohm cable to extend the end of that to the transmitter.